This is the motet Spem in Alium by Renaissance composer Thomas Tallis. While most choral works are written for 3, 4, or maybe 5 parts, this work is written for a remarkable 40 parts. So you are forgiven if you weren't able to follow everything that was going on in that dense excerpt. The complexity of this work mirrors the complexity of the subject we will study in this video, random processes. So far, we've looked at just one or two random variables at a time. With random processes, we will graduate to looking at infinitely many random variables at once. This lesson represents a new chapter in this course, so I think it's worth spending some time framing how random processes fit into the broader narrative of the course. At the very beginning of this course, we introduced the idea of random variables, but we only looked at one random variable at a time. For example, our random phenomenon might be the repeated tosses of a fair coin. We might be interested in the random variable x, the number of tosses until the first heads. Here's a schematic that hopefully helps explain what's going on. The underlying random phenomenon is the repeated tosses of a fair coin. Each possible outcome is an infinite sequence of heads and tails. So, one possible outcome is tails, heads, tails, tails, heads, and so on. If this is the outcome that was observed, then the random variable x would equal 2. On the other hand, if we had observed the outcome tails, tails, heads, heads, tails, then the random variable x would equal 3. And so on. If this had been the outcome that was observed, then the random variable x would have equaled 1. The idea is that for each realization of the random phenomenon, we only observe one number. And we studied properties of this one random variable. For example, we know that x, the number of tosses until the first heads, has a geometric distribution. From there, we then moved on to pairs of random variables, talking about things like joint distributions and covariance. For example, if we again consider repeated tosses of a fair coin, we might be interested in x again, the number of tosses until the first heads, as well as another random variable y, the number of heads in the first 5 tosses. In other words, for each realization of the underlying random phenomenon, we observe two numbers now, x and y. On their own, x follows a geometric distribution and y a binomial distribution. But the two are obviously not independent. For example, knowing that y is greater than 0, that there was at least one head in the first 5 tosses, gives us information about x. It tells us that x must be less than or equal to 5, that 5 or fewer tosses were needed to get the first heads. By studying the two random variables together, we can uncover the relationship between the two. That brings us to today's lesson. We're going to move beyond 1, 2, or even 3 random variables at a time. We are going to go straight to studying infinitely many random variables at once. That is, we are going to consider cases where we observe an infinite collection of random variables xt, which we will think of as being indexed by time t. For example, if we again consider repeated tosses of a fair coin, xt might represent the outcome of the tth toss, so 1 if the toss is heads, and 0 if the toss is tails. So for this outcome, we'd observe infinitely many values. x1 is 0, since the first toss is tails. x2 is 1, since the second toss is heads. x3 is 0, since the third toss is tails, and so on. For this outcome, we'd observe a different set of infinitely many values, and likewise for this outcome. If we think of these random variables as indexed by time, each outcome gives us an entire function of time. This collection of random variables is called a random process. Because it is indexed by time, we can also think of it as a signal, specifically a random signal. Another term for a random process is a stochastic process. The word stochastic is just a synonym for random. The random process of coin tosses, xt, that we just saw, is an example of a special type of random process called a Bernoulli process. In a Bernoulli process, you observe an independent Bernoulli random variable at each time t. So one possible realization of this process might look like this. Remember that each outcome gives you an entire function of time, so we can graph that function. At each time t, you observe a Bernoulli, so the only possible values are 0 and 1. Now here's another possible realization of this process. Of course, there are many others. Now, if we slice this process at any particular time, say at time 2, then we just get a single random variable, and we can study it just as we would any other random variable. For example, we can ask what its distribution is. This random variable has a Bernoulli distribution with p equal to 0.5. That's just how the process is defined. And it has two possible values, 0 and 1, with equal probabilities. So its PMF looks like this. I've drawn the PMF sideways so that the possible values line up with our graph of the random process. Now, we often classify random processes based on the possible times and the possible values. The Bernoulli process is an example of a discrete time process because it is only defined at integer times t. And another way to denote a discrete time process is to use the general notation for a discrete time signal with square brackets instead of parentheses. Now, the Bernoulli process is also an example of a discrete valued process, because if we slice the process at any time t0, we get a discrete random variable, specifically a Bernoulli random variable. Now, we'll see some examples of continuous time and continuous valued processes in follow-up videos and activities.